Welcome to YouTube channel scientific underscore math. In this lecture, we are starting a new topic that is eigenvalues and eigenvector. Okay, so in the first lecture of eigenvalues and eigenvector, we have the learning objectives that are the definition of eigenvalues and the eigenvector, represent graphical representation of eigenvalues and eigenvector, and third we have example. We will also solve one example related to the eigenvalues and eigenvector. Okay, so let's start our first lecture about the eigenvalues and the eigenvector. So, eigenvalues and eigenvector. First, we discuss the definition, and we have a definition. If A is an n cross n square matrix, then a non-zero vector x in Rn means a real coordinate space of dimension n is called an eigenvector of A if the product of the matrix A with the vector x is a scalar multiple of x, that is okay. So here we can see that this is the matrix A and this one is the vector, and the product of this one is equal to the scalar multiple of the vector x. Okay, so here we have the condition, that is the vector uh, cannot be equal to 0. Okay, so uh, the product of the matrix A with the vector x is again vector x with the scalar multiple. Okay, so for some scalar, that is lambda, the scalar lambda is called eigenvalue of the matrix A, and x is said to be an eigenvector corresponding to the eigenvalue, that is lambda. Okay. Note, here we have a note, an eigenvector must be non-zero, okay, in order to avoid the irrelevant case, that is the product A into 0 is equal to lambda into 0, which is hold for every A and lambda, means the vector x cannot be equal to 0. Okay, so we will discuss in detail in next lecture. Okay, so next we have in general a vector's reflection or image. Okay, after being multiplied by a square matrix A differs from the original vector, means when we multiply the vector x with A, which is equal to lambda into x. Okay, so after being multiplied by the A matrix, image of this vector, okay, will be differ from the original in both magnitude and direction. Okay, we will see this one with the help of graphical representation. Okay, so however, in special case where x is an eigenvector of a multiplication by the A matrix leaves the direction unchanged. Okay, so there will be maybe some special case when we multiplied the matrix A with the x that leaves the direction unchanged, means the direction of the vector will be not change after multiplication by the matrix A. Okay, for example, in R2 or R3 real coordinate space of dimension 2 and 3, multiplication by A maps each vector x of A along the same line uh, through origin as x. Okay, so this depending on the sign and magnitude of the eigenvalue lambda corresponding to the eigenvector x. Okay, so here we have the operation, that is the product of matrix A with the vector x, which is equal to some scalar into the vector x. Okay, what happened when we multiply the matrix A with x? Okay, which compresses or stretches the vector x by a factor of lambda. Okay, here we can see that when we multiply the uh, met, uh, vector x by the matrix A, this will this is equal to lambda into x, and here lambda is some scalar, okay, that is the eigenvalue, and again the vector, that is the eigenvector. Okay, so this multiplication do compresses or stretches the vector x by a factor of lambda with a reversal of direction in the case where lambda is negative. Okay, so let's see this with the help of uh, graphical representation of eigenvectors, eigenvalue. Okay, so here we can see that the first case is this one is the vector, original vector x. Okay, so after multiplication, the is the matrix A that is equal to lambda into x. Okay, so in this case we can see that this vector is compressive. Here we can see that the lambda into x is compressive. Okay, and this multiplication of the original vector with a of lambda. Okay, so here we can see that the vector from origin to, and after multiplication vector x by the matrix A, and this compares the vector by the vector of lambda. Okay, so we can see that the magnitude of this one is less than the original vector. Okay, so this one is the first case, and next we can see that here we have after the operation or the multiplication of the matrix A with the vector x that is equal to lambda into x, and in this case the matrix S is stretches by a factor of lambda. Okay, so here we have one, a original vector x that is in blue color from origin to here over to, yes, and after multiplication with the matrix, and we can see that the vector x stretches, okay, with the factor of lambda. Okay, so this one is the case second. In this case the vector is stretches, and in this case the vector is compresses. And third case we have, case third we have, okay, and we can see that here we have the original vector x in blue color, and after the operation or the multiplication of vector x by the square matrix A, this will be equal to some scalar into the original vector and with the reversal direction. Okay, so we can see that in this case the vector that is minus lambda into x in opposite direction to the original vector, and also we can see that this one is also compresses. Okay, so this one is the third case, reversal direction and reversal direction and compresses. Okay, so we have the fourth case, that is we can see that after the operation and after the multiplication of the vector x with the matrix A, that is equal to some negative scalar and with the vector x, and in this case we can see that here we have the original vector x, and this vector minus lambda is that is equal to in reversal direction with these stretches. Okay, we can see that the vector is stretches, the vector x is stretches by the factor of lambda and in a reversal direction. Okay, so this is the uh, operation when we apply the operation with the that is the multiplication of the matrix A with the vector x that is equal to some scalar into the vector, again vector x, and what will happen after multiplication, the vector will compresses or stretches, or the direction will change, shift in direction when the uh, lambda is negative. Okay, Now we discuss example. Okay, so we have an example, and uh, let's the matrix A is equal to this one 3 0 and 8 minus 1. Okay, so here we have compute the product AX for x is equal to 1 2, that is the eigenvector corresponding to the value lambda is equal to 3. Okay, so after multiplication, what do you notice about this product? Okay, so we have also replied about this one and also this one. Okay, so in this lecture only we will discuss the graphical representation or about the operation what will happen when we multiply the vector x with the square matrix, and this will equal to some scalar with the vector x. Okay, so in next lectures we will also solve the example how we can find the eigenvalues and the eigenvector. Okay, so let's solve this example. Okay, so first we compute this product for the eigenvector, and this one means ax is equal to this product. Okay, so ax is equal to, okay, here we have the matrix A and this one is the eigenvector, and after multiplication we get again a vector. Okay, so this is equal to, we can take common from uh, this vector, that is 3, and which is equal to 1 2. Okay, so we can see that this is our original vector x. Okay, so which is equal to 3 times the original vector x. So in this case, the product A yielded a vector that is 3 times yielded. We can see that yielded a vector that is 3 times uh, 3 times the actual vector x. 3 times the actual vector x. We can see that this is our actual vector x, and this is 3 times the actual vector x. This product. Okay. So geometrically multiplication by A has stretched the vector x by a factor of 3. Stretch the vector x by a factor of 3. Let's see this with the help of graphical representation. Okay, so we can see that this is our original vector x eigenvector corresponding to the eigenvalue lambda that is equal to 3. Okay, so after multiplication we can see that this original vector is stretched by a factor of 3. Okay, after multiplication, that is our new vector, that is 3 times the original vector x. Okay, oh, and here we have the uh, eigenvalue, that is 3. Okay, so we can see that the graphical representation and of eigenvalues and eigenvector, what happened after the this operation when we apply the when we apply this operation on the vector x, that is equal to the some scalar lambda value into the x. Okay, so thank you so much for watching my video. Please subscribe my channel scientific underscore math, and in next lecture we will discuss in details why the vector eigenvector cannot be equal to 0, and we will also solve examples how we can find the eigenvalues and eigenvector. Okay, so thank you so much for watching my video. Please subscribe my channel scientific underscore math.